All right, so today we're going to be finishing up section 4.3, moving on to section 4.4, and finishing that up because that's a short section. And then from there, we'll probably dabble a little bit in section 4.5. And then after chapter 4, 4.5, 4.6, and I think 4.7, these are going to be some short things here. We'll be moving on into chapter 5. But as you just had your test and we are working on grading your test, we will have that back to you by Thursday. So to let you guys know, it takes us a while because of the style of test I give. I don't do multiple choice in a class like this. This one's that free response. It takes a while to grade this kind of stuff. But we'll get that thing back to you guys ASAP, and it'll be on Thursday. The other thing, like I said, is because we're working on this stuff, and I continue to move on into chapter 4, let me put it on the student view here so you don't see all of the stuff I've got waiting in the wings for you guys. If you come over here to modules, I think is where I put everything, here's those awesome videos that you guys seem to like of mine. And then don't forget about the PALS program and stuff like that. So if you need some extra help with this stuff, please attend that and give them a report on the PALS program. Let me know how they're doing over there. But what are we up to? Homework number, there it is, number 5. Already waiting for you guys. Homework number 5 is on sections 4.1 through 4.4. So I'm about to finish this up, but I waited to open this thing up until yesterday because we had the test, and I didn't want you guys focusing on this while you should be focusing on the test material. So I've added an extra week, so this thing's not due until November the 17th, okay? And of course, if you got the traditional homework also on 17th, so here's your traditional homework, your paper pencil one. This is the online homework, but they're both due on the 17th. So pay attention to due dates and stuff like that. And then after that, I will give you one on the rest of chapter 4 and a little bit of the chapter 5 material. And then after chapter 5, I hope to dabble in a little bit of the chapter 6 material. But then from then, we're going to have our last test and then, of course, ready for the final exam. So, that's the last good month of the class and stuff. So, all right, let's go back over here. Let's leave the student view and go over here to my .cam. All right, and let's pick up where we left off last time. We were left off last time with focusing on bases, okay? So let's pick it up where I left off, and I was going to ask you guys some questions and about things like standard bases versus other bases and things. And I'm going to try to describe to you guys why we need all this stuff, what the real point is. And you guys being mostly computer science majors in this class, this semester anyway, I usually have a bunch of engineers and stuff, but I think I have majority of computer science and computer engineering majors in here. So I want you to see kind of the point of this, why we do what we do and why it's important to you guys. So first off, we're talking about your standard R3. What is the standard basis for R3? What is a basis? That means it's a minimum number of vectors that when I do so they got to be linearly independent, and when I span, take a set of linear combinations of those vectors, I'm guaranteed to get every vector that is in R3. What is your standard basis? How about you tell me? Well, right idea when you put it together, but what are the vectors? In R3, it would be the vector 1, 0, 0. 0, 1, 0, and 0, 0, 1. That is the standard basis in R3. And notice with R3, I've got 3 components, okay? So 3 components really dictate the size of the vectors and stuff. Now, from there, I should open this thing up. Hold on. There we go. You can see it a little bit better. There we go. All right, so for R3, what's the standard basis? 1, 0, 0, 0, 1, 0, and 0, 0, 1. And notice there are 3 components making up the R3, and if I do any linear combination, I can get any vector in R3. Let's make up one. Alpha, beta, gamma. Alpha, first component, second component, beta, third component, gamma. So I take alpha times the first standard basis, plus beta times the second element of my standard basis, plus gamma times the third element, and the 0, 0, 1s and the 0, 1, 0s and 1, 0, 0s gives me the alpha, beta, gamma. So I can create any vector in R3 off of these 3 guys. But these are the standard bases. These are the ones that are most logical and easiest to see. But we have, other than just plain old Rn, we got other kind of vectors. So for example, in vector spaces. Now, for the vector space Pn, Pn is the set of polynomials of degree n or less. So, polynomials, P, for math people, don't think too deep in this. Polynomials of degree n. N may be 3, so degree 3 or less. That's a degree 3 polynomial, degree 2 polynomial, degree 1 polynomial, and the constant polynomials, okay? So, with the degree n, so P of t, P being the polynomial, is A0, that'll be your constant, plus A1 times t, plus A2 times t squared, plus dot, 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 plus AN times t to the n. So an example here, for example, Pn 3 plus 4t minus 6t cubed, this would be a polynomial, and Pn, as long as the n has got to be 3 or bigger, okay? This is a cubic polynomial, so it's got to be a P3. If I did a P2, this vector would not exist because you're stopping at 2. So the degree has to be basically identified. Here, the 3 is the degree. So here, for your Pn, n's got to be greater than or equal to 3. What would the standard basis of this guy be? Well, what's the standard basis in Rn? Catch a pattern. It's 1 in the first component, 0 is everywhere else. Second one is 1 in the second component, 0 everywhere else. And for the third component, 1 in the third component, 0 everywhere else. So if you look at this guy right here, what would a standard basis of Pn be? It would be the set, let's call it S for set, of vectors. It would be the Tn, that would be the coefficient of, that would be 1 t sub n, and everybody else is 0. It would be T n minus 1, imagine that guy 1, t to the n minus 1, comma, dot, 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 comma, t squared with a 1, t, 1t, so A1 would be 1t, and then the last one, I need a constant, but we want standard, so we just make a 1 for that particular position. Okay? And then I want you to notice that obviously S spans all of Pn. Okay? Any linear combination, I can get any polynomial back again. So I just looked at each coefficient, and basically I'm doing the same thing. I'm doing the 0, 1 stuff. So for my constant, I made him 1 and 0s everywhere else. For the t term, I want a 0 constant, a 1 for the t term, and a 0 everywhere else. This gives me just the t, and that's how I got the rest of it. Got a question for you. I'm going to be talking about this later on throughout the talk on this stuff, but here's a great time to bring it up. What is the dimension of Pn? Oh, let's go back up here. What is the dimension of R3? Let me talk about that. The dimension of a space is the number of vectors in the basis. You need that in your notes. That's something important. The dimension of a space is the number of vectors in the basis. So, what is the dimension of R3? Don't hurt yourselves. 3. Not because there's 3 components here, but it is connected, is the fact that we have 3 bases. 3 basis vectors. Does that make sense? 1, 0, 0, 0, 1, 0, 0, 0, 1. So yeah, because there's 3 components, that also means the dimension of R3 is 3. But you can talk about things like the dimension of a subspace, right? You can, you look at the basis and the dimension of the basis. So the vectors may come from R3, but if I only got 2 vectors in subspace H, the dimension of subspace H would be 2 because there's 2 vectors in the basis. Does that make sense? Question for you. What is the dimension of Pn? What is the dimension of Pn? Pn being the set of polynomials of degree n or less. What would it be? No, nothing by. We're not talking about matrices here. We're talking about the number of components, vectors, if you will, number of vectors in the basis. N plus 1. Why plus 1? Well, you've got t, that's your first one, t squared, there's second one, all the way up to tn. So that makes n of them, but with that constant, that's t0, if you think about t raised to the 0 power, which is 1, a constant, there's actually n plus 1. So just a little side note, the dimension of p sub n is actually equal to n plus 1. However, the dimension of R3 is 3. Just some little side notes about, again, when we get into this, where again, we're talking about bases. So a natural concept is the dimension, which is the number of vectors in the basis here, okay? So now, why is this guy a basis? How do I check for a basis? To check for a basis must be linearly what? Independent. Now, this is what I'm trying to drum into your head. How do I check for linearly independent? How do I check for linearly independence? Well, it's a standard thing. You put arbitrary constants in front of your basis elements, basis vectors, and you set it equal to 0, and then you solve for those constants. And if the only answer you can get is the first constant has to be 0, the second constant is 0, all the constants are 0, then they're linearly independent. If I get one constant that's not 0, then I actually have a linear dependent system. I can move that vector to the other side and actually be able to solve one vector in terms of the combinations of the other. That's called linearly dependent. So here we go. So I'm checking for S here. So I'm going to take C1, multiply it times 1 plus C2 times T plus C3 times T squared plus plus Cn minus 1 times T to the, look at the pattern here, n minus 2 plus Cn times T to the n minus 1 plus Cn plus 1, because there's actually n plus 1 vectors here, times T to the n plus 1. I'm going to set it equal to 0. I want you to solve for the CIs. What do they have to be? If you got a polynomial that is always 0. Oh, n plus 1. That'd be n. That's a typo here. I was 4 steps ahead thinking about lunch. Okay, so t to the n. Sorry about that. You're right. That's t to the n minus 1. That's t to the n because that's where you stop at. There you go. Okay, sorry. Thank you for noticing that. But my point is this. How does a polynomial always equal to 0? There's only one way. I mean, we're talking about these guys are components here. What kind of C's do you get? Well, the only way you can get the equal to 0 is it's got to be equal to 0 plus 0t plus 0t squared plus 0t cubed plus plus 0t to the n, which would imply that the C1 has to be 0, C2 has to be 0, C3 has to be 0, Cn has to be equal to 0, and because there's n plus 1 of these guys, Cn plus 1 has to be equal to 0, which implies, thus, okay, the set S are okay, which means that as long as I have a linearly independent system that clearly spans all of, in this case, Pn. So S spans all of Pn. S is linearly independent. 3 dots in a triangular fashion means therefore S, which is equal to the set 1 t squared t to the n minus 1 and t to the n basis for Pn. Okay? So, from there, we naturally go to a theorem. Okay? So this, and what does it mean to be, again, a basis. What are the two things I had to show? I had to show the set spans all of whatever space that I'm trying to talk about. That means any vector within the space can be written as a linear combination of these guys. And the elements that in the thing that I want to show as a basis have to be linearly independent. So I have to show spanning and I have to show linear independence, and between the two, I get a basis. That's your definition. Okay? So from here, the natural progression is, of course, a theorem. This is called the spanning set theorem. It says this: let S be equal to V1, comma, V2, comma, dot, 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 out to VP, be a set of vectors in V, and, sorry about that paper there, and let's let H be equal to the span of V1 through VP. Okay? Now, let me stop there for a second, because I'm trying to make this connection for everybody. We know from previous material, all the way from chapter 2 on, that when we span means a set of linear combinations. And the span of any set of vectors is always a vector space. Does that make the vector V1 through VP, does that make these vectors a basis? No. I never said these guys were linearly independent. They may be very linearly dependent. I mean, I can write one as a linear combination of the others, and maybe several of them I could write as a linear combination of the other. All I'm doing is linear combinations of these guys. The span of any set of vectors always makes a space. But then, A, if one of these vectors in S is a linear combination of the other vectors, then if you remove that vector from S, the new set is still spans H. If you got a linearly dependent vector in your group of vectors, you can just chunk him out, because the spanning set, the span, which is all the linear combinations, well, you've got linearly dependence here. If you remove one of them that's dependent on the others, they're still going to span the entire set. Okay? So remember that. So because we're going to be figuring out how to create a basis. The first thing you do is you figure out if they're linearly independent or dependent. If it's dependent, you start moving out, basically getting rid of the ones that are dependent, and then going back and looking at the rest of the vectors and see if they're linearly independent or not. You've got to have linearly independence to be able to create a basis. The second thing, part B here, is this. If H is not equal to the trivial zero vector, then some subset of S is going to be a basis for H. There's a basis out there. I don't know if it's this set right here. If I remove the VP, is that going to be the basis? Maybe I need to remove a couple more of them. But until I get it down to be a set of linearly independent vectors that actually spans all of H, I've got to keep removing that until I get that, and then I actually have a basis. So, how do we figure this type of thing out? Well, all right. Well, in terms of standard basis and stuff like that, let's go to our basis for things that we know. So let me underline this one. What about a basis for a null space of A? Now, you should know, we beat it to death on the last test, and even before the last test, the idea of null space, okay? So the null space is this. You write a solution for AX equals the 0. That's how you get the null space. You're basically going to solve this thing for X. And you write in parametric vectored form. So you basically, what do we do? Let's go through the steps. You take matrix A, you augment it with 0, if you like, and then you reduce row echelon form this guy, and then you rewrite them as equations and solve for the pivots. And you get a combination of solving for the pivots, and they're going to be equal to a bunch of terms that have free variables in it. Does that make sense? And then you pull out those free variables, and you got the quote-unquote coefficients, which create your basically your basis for the null space. So the vectors of coefficients of the free variables are the basis vectors. It's what we did to create the basis vectors. What about for the basis for the column space of A? What do we have to do with that one? Okay? So what we did on that one was we looked at the pivots. Okay? We went ahead, took matrix A, we row reduced that sucker, and we looked at the pivots. and only the pivots created a basis for the column space of A. We had to go back to the original matrix, because this was reduced row echelon form. We figured out the ones that we needed for the basis based upon the location of the pivots. Then we went back to the original matrix, grabbed the column vectors where the pivots came from, and put the word span in front of it and declared victory that we had the space. And we also, those set of vectors where the pivots came from, created the basis. All right? So, let's come over here and let's do an example. Okay? So for this one right here, I got two good examples here, so let's start with this first one right here. A, let A be this matrix. 1, 1, 5, 0, negative 5, negative 10, negative 3, 2, negative 5. And again, this is me trying to be more poignant like we did on the last test. What is the column space of A? Column space of A equals. Now write the column base in terms of a basis, okay? Now, subtle difference. This is what I want to show you guys. Could you please tell me what the column space of A is? Well, the column of A, column space of A. This would be the span of the vectors 1, 0, negative 3, 1, negative 5, 2, 5, negative 10, negative 5. Officially, that is what the column space of A is. What is the column space? It is the span of the column vectors. All I did was take the vectors out of my matrix, the column ones, and put the word span in front of it, all right, and wrote them as vectors, column vectors, okay? Is this a basis? No, not necessarily. Maybe. How do I figure it out? Well, now, write the column space of A in terms of a basis. So what I want to do is I want to take back to my matrix A. This is 1, 1, 5, 0, negative 5, negative 10, negative 3, 2, negative 5. And let's go for the reduced row echelon form so we can figure out who the pivots are going to be located at. Pivots are going to be the key. These are the ones you need to have for that linearly independent aspect. Now, and you don't even have to go for a reduced row echelon form. You can stop a little bit short, but that's just, you know, really bothers me because when you're going to go for a echelon form, let's go for the reduced echelon form because it's awesome. All right, so here we go. Help me out here. What do I need to do to this thing? Well, I try to make it nice for you guys. So there's one move I'm going to make, and what is that? 3 times row 1, add it to row 3, replace row 3. I'm going to sweep down and kill off that negative 3. That makes it 1, 1, 5, 0, negative 5, negative 10. Here we go. 3 times 1 is 3, plus negative 3 is 0. 3 times 1 is 3, plus 2 is 5. 3 times 5 is 15, plus negative 5. 15 minus 5 is actually 10. There I go. What would your next move be? So I got, now the new matrix is 1, 1, 5, 0, negative 5, negative 10, 0, 5, 10. What would your next move be? Yeah, I wouldn't go for the pivot thing here. You can if you want to, but I noticed that these two guys are equal but opposite. So why don't I just sweep down and just basically take row 2 and add it to row 3 and replace old row 3 with that? What would that give me? 1, 1, 5, 0, negative 5, negative 10, 0, 0, 0. What would your next move be if we're going for, well, let me stop here for a second. What do you call this setup of matrix? What style is it? It's not reduced row echelon form, but it is something you should recognize. What is it? It's echelon form, right? Row echelon form. This is officially REF. It's not RREF, it's REF. With REF, your pivots do not have to be ones, but the pivot positions have to be earmarked with zeros below it, and that's it. Where are the pivots at? This one here and this one here are my pivots. Does that make sense? So I'm done, basically, because I've got my pivots, and now I got it done. But if I go for, just to show you, how far you can take this, if you want to continue on, I would now multiply -1/5 times row 2, and that would give me 1, 1, 5, 0, 1, 2, I believe, if I did my math right, 0, 0, 0. And then I would do one more move, and that would be -1 times row 2 added to row 1, replace row 1 with that, and that gives me 0, 0, 0 on the bottom, 0, 1, 2, and then just add, that'll be 1, 0, and then -2 plus 5 is 3. So, this is now RREF. This is why in chapter 1 we kept beating this concept to death on knowing the difference between the two. My point to this exercise is this: whether you just stop here, and sometimes it's advantageous, saves a lot of time on a test or whatever. If I can just go for REF, I know where my pivot positions are. REF, it makes it real obvious, it's where the ones are located at, with me, as you focus down the rows, because this is reduced row echelon form. But they are located in the same spot, which is the first and second vectors. So, back to the question. Now, write the column of A, there it is, column of A, in terms of a basis. It will be the span, because this is a space, so it's the span of what would the actual basis for this column space of A be. Well, which vectors do you actually need? The first vector and second vector. It's actually these vectors here. 1, 0, -3, and 1, -5, 2. Does that make sense? This is a basis, and the span makes the space. Got a question for you. See if you learned anything. From what I talked about before, could you please tell me what is the dimension of the column space of A? Fill in the blank. It is 2. But I would not have known that without actually doing what I just did, because if I looked at this set, most people say, well, the dimension of the column space of A is actually 3. No, it's a subset of R3, I'll give you that, but subspace of R3, I'll give you that, but actually the dimension is 2 because there's 2 vectors in the basis. This is not a basis. That third vector is actually a linear combination of the other two, so this is a linearly dependent. Does that make sense? So, here we go. Let's look at this guy here. Let's let matrix A be 1, 0, -5, 1, 4, -2, 1, 6, -2, -2, 0, 2, -8, 1, 9. What size matrix is this guy? I'll help you out. It's 3 by, what's the rest of it? 5, okay, 3 by 5. Does that make sense? Okay. I want you to find a basis, in terms of basis, that's the key word. In terms of a basis, I want you to find the column space and the null space of A. All right. So we'll do this in order, but the first thing I'm going to do here, if I'm looking for a null space or a column space, and for that matter, a row space, the first thing that I want to do, if I'm looking at it in terms of a basis perspective, I want to know who are my linearly independent vectors. And I find that from the reduced row echelon form, or at least REF, row echelon form. So the first thing I'm going to do here is I'm going to go for, and I might as well use the RREF, and I'm going to give you this one just because this would take a little bit more time to actually row reduce here, but I get this. 1, 0, -5, 0, 7. I get 0, 1, -4, 0, 6. And I get 0, 0, 0, 1, -3. So I'm going ahead and mathematically, okay, I use my calculator, give you the RREF on this guy. All right? Once I've got that, now I can go get my spaces. So, here we go. In terms of a basis, what is the column space of A equal to? Fill in the blank. Well, it will be a span because this is the column space. Space requires a span of, and here it is. This will be my basis. What's my basis? Well, where are the pivots located at? First vector, second vector, as I'm going column space, looking down, and which one? 1, 2, 3, and the fourth vector. Does that make sense? Notice the pivot. Pivot, pivot, and pivot. So the span would be, back to the original, all I need is the 1, negative 2, 0. I need the vector 0, 1, 2. And I need the vector 1, negative 2, 1. These three vectors form the basis for the column space of A. Did I lose you guys anywhere? Okay. Now, could you please tell me the basis for the null space of A? So I'll write them over here. The null space of A would be equal to the span of a set of vectors. Now, for the null space of A, you got to work a little bit harder, because what does the null space stand for? Okay, so let me just draw this kind of. All right, so for the null space of A, the null space of A implies that A times X equals 0. Well, I went ahead and did my row reduction, so I'm going to rewrite this as equations. This would be the x1, x2, x3, x4, x5. So I get x1 minus 5x3 plus 7x, 1, 2, 3, 4, 5, x5 equals 0. Remember, null space. I didn't augment it with 0, but do you really need to? Think about it. Okay, so what about the next equation? It's going to be x2 minus 4x3 plus 6x5 equals 0. And the third equation is, this is 1, 2, 3, 4, x4 minus 3x5, I did kind of line these guys up, equals 0. Does that make sense? Now, how do we find the null space? Same thing as what you had on your last test. You solve for the pivots. Who are my pivots? x1, x2, and x4. So these are the pivots. So x1 would be equal to, moving to the other side, 5x3 minus 7x5. Solving for the pivot. x2 would be equal to 4x3 minus 6x5. Solving for the pivot. Now, this is x3, x4, and x5. You're going to be solving for all of them. But wait a minute, some of them are free variables. But x3 is not a pivot, so he'll be equal to x3. x4 is a pivot, so he's equal to, moving to the other side, 3x5. And x5 is not a pivot, so he's equal to himself x5. And I am trying to line these guys up so you begin to see the parametric vector form. So this tells me pretty much, writing it down here, you have x1, x2, x3, x4, x5 equals, on the x3, I got 5, 4, 1, 5, 4, 1, 0, 0, because there's nothing there, times x3 plus negative 7, sign goes with it, negative 6, there's no x5 term here, so that would be 0, 3, and that's a 1, x5, 1, x5. And if you think about it, this is the set of linear combinations, because x3 and x5 are your, it can be any constant in the world of whatever space you're playing with in terms of the scalars. So what exactly is the span, what is the null space of A? It is the span of these vectors. It is 5, 4, 1, 0, 0. And the other vector is negative 7, negative 6, 0, 3, 1. Does that make sense? And these guys are the bases. Does that make sense? Got another question for you. I'm drumming an idea in your head because I'm going to be talking about this later on. Could you also please tell me what is the dimension of the column space of A? And by the way, what is the dimension of the null space of A? Go. Column space of A is 3. Null space of A is 2. Okay? And there's a big formula coming down the road that you can mathematically always calculate these things because they're gonna match up to something or other. And what it really is this. What was the size of this matrix A right here? 3 by 5, M by N. So the dimension of the column space plus the dimension of the row space will always be equal to N. M by N matrix is always going to be equal to that N, which is 5. 3 plus 2 equals that 5. That will be a theorem coming up later. Okay, it's a very helpful mathematical formula when you're analyzing this stuff. Did I lose you guys anywhere? Questions? All right. Now, from there, let's move on into section 4.4. So that was a nice little review. Okay. Several pieces of paper down here together because, okay, section 4.4. All right. We're going to be looking at what we call coordinate vectors. Okay? So, definition. Let beta, we're going Greek on you, so be prepared. Let beta equal B1 vector, comma, B2 vector, comma, dot, 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 Bn vector. And this is a basis for vector space V. And let's let X be an arbitrary vector in V. Okay, so I got this basis. And we're not very standard here, so B for basis here. B1 vector, B2 vector, out the Bn vector. This is a basis, which means these guys are linearly independent here. It's a basis for V. And X is an arbitrary vector here. Then, the coordinate of X relative to basis B are the coefficients C1, C2, dot, 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 out to Cn, such that X equals C1 times B1 plus C2 times B2 plus dot, 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 plus Cn times Bn. And we have a notation. See, we have a vector X, there's X, but when you put the little brackets around there with a subscript beta, meaning for the standard basis beta, it's going to be these are going to be the coefficients, C1, C2, dot, 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 out to Cn, and we write it as a column vector. Okay? So, before I explain what exactly is going on, let me show you some examples just to get it clear. And then I'm going to try to make it relevant to you and why you need to know this stuff. So, I have an example. Okay? So here's my example. All right. I've got the vectors 1, 2, 3, 4, comma, negative 1, 1, 0, 1, and the vector 3, 1, 0, 0, elements of R4. And I'm going to give you, given, they are linearly independent. These are linearly independent vectors. Okay? Merry Christmas. So let H be equal to the span of these vectors. 1, 2, 3, 4, negative 1, 1, 0, 1, 3, 1, 0, 0. And so this is a basis because they're linearly independent. And when I take a span of a linearly independent set, that creates a vector space. In this case, a vector subspace H of R4. All these vectors are coming from R4. And I'm going to call this guy, just because I like to name these guys, this is B1 vector, this is B2 vector, and this is B3 vector in order. Okay? Now, find X, element of H, such that x coordinate relative to basis B is equal to -1, 2, 3. Now, I'm doing this one for a reason because here's the big deal. This stuff can get very confusing if you're not paying attention to the number of vectors and the basis and stuff like that, and the number of elements and the components. You've already seen this confusion about what's the dimension of the space and where does the space come from type thing here. So look at this guy. These are vectors from R4. So they have 4 components. But we're focusing on just these 3 linearly independent vectors, creating a subspace H. And so this is my basis B. So I want to find X, element of H, such that B vector is, the coordinate of the X vector relative to basis B is the vector -1, 2, 3. I've got no imagination, so it's 1, 2, 3. I thought you guys would be not very happy with that, so I made it -1, so you can see the numbers. -1, 2, 3. So C1 is -1, C2 is 2, and C3 is 3. So to figure out the X vector, these are the coefficients. This is what we mean by this coordinate. These are the coefficients. So this is a coordinate vector, if you will. Notice it's only got 3 components. You know why it has 3 components? Because I only got 3 basis vectors. Does that make sense? These are the coefficient of the basis vectors. That's why order is important. So this will be -1 times that first vector, plus 2 times the second vector, plus 3 times the third vector. So it's -1 times 1, 2, 3, 4, plus 2 times -1, 1, 0, 1, plus 3 times 3, 1, 0, 0, and then you just multiply and add, and you get the vector 6, 3, -3, -2. This is a vector in H because it's a linear combination of my basis vectors, and this is in the subspace of R4. Notice that this is the vector X that is inside of H. This guy here, -1, 2, 3, that is not a vector inside of H. These are just coordinate vectors. Does that make sense? So here it's nice because you can see that they're different sizes. This is some vector with 3 components. This is a vector with 4 components, which is coming from the subspace R4, but because it's a linear combination of basis in H, it's actually an element of H. Does that make sense? Now you ask yourself, why do you care? All right, think of it like this. You're trying to rewrite vectors in terms of a certain basis, okay? But the standard basis is real easy, okay? So let me see if I can show you the standard basis type thing here. All right, turn it over here. So I want you to see this. The standard basis is not real exciting in terms of coordinates. Let me show you. So here it is. All right, note, the standard basis, we'll call it epsilon, which is going to be the E1, comma E2 for R2, where E1 would be 1, 0, and E2 would be 0, 1. These are elements of R2. This is your standard basis. So if you write an arbitrary vector, let's say that you have the same thing what we did before. I'm going to give you a coordinate vector. There it is. -1, -2. So this is C1 is 1, C2 is -2. This is your coordinate vector of E. I want to figure out what the coordinate, this is coordinate vector of vector X here. This is the coefficients. 1, C1 is 1, C2 is -1. Of your standard basis, this would be 1 times 1, 0, plus -2 times 0, 1. And what do you get? I get the vector 1, -2. Now let me show you what I'm talking about. I'm saying this is your, quote, coordinate vector. These are the coefficients of the standard basis of R2, 1, 0, and 0, 1. But when you look at the coordinate vector and you look at the vector itself, what do you notice? It's the same thing. Now let's talk about code theory. That's usually a big topic, especially this day and age, when you talk about credit cards and all that good stuff that we have to hide ourselves from people trying to steal our stuff. I talked to Dr. Hetye just a little while ago before class, and he was talking about somebody in Orlando was using his credit card. He hasn't been to Orlando in quite a while, but yet somebody's charging something on his Discover card yesterday. So we had to call up the Discover card, explain to them, this wasn't me, I'm not in Orlando, haven't been to Orlando, and so they had to cut off thing. Identity theft is what I'm going at. So this is something you guys need to be paying attention to. So what do we want to do? Well, we want to do code theory, which means I want my credit card numbers, so when I type them into the computer, when I'm buying crap off eBay or whatever it is, okay, Amazon these days, I want them to hide my information so hackers don't get it. Well, if you're using the standard basis of whatever system that you're working with to actually code stuff, pretty pathetic. Okay, it's not really hiding anything. The coordinate vectors is the actual vector when you're using this world. That's not really, disguising anything. But if I come back over here and start to talk about coordinate vectors on a different kind of a basis type thing here, then this really is kind of concealing what exactly the vector that I'm interested in, that I'm trying to hide, is really. I got to be able to read it, but I don't want anybody else to read it. So these are my coefficients. I got to know what the basis is, and if it's not standard, well, that's where the hackers are looking for to try to figure out how they're manipulating this stuff. So I put my coefficients in front of the vectors that I know from my basis, and I can recreate that X vector. That would be my credit card numbers, or whatever the case may be. You can see the power of this stuff and why you need to know this stuff. This really is, this idea of coordinate vectors is really trying to hide this stuff. But, so, in the wonderful world of standard basis, the coordinate vector with a standard basis would be the same thing as the vector itself. So with a standard basis, we just drop the little epsilon here, and because your coordinate vector is the vector when you use a standard basis. Nothing is really being hid. It is basically your code in the clear. You can read the credit cards right off the bat because the coordinates are your credit card numbers. Does that make sense? So this is why standard bases are cool. They're easy to manipulate, but that's not reality. This is not the world we really want to play in, because it gives you exactly what you want. So, quote, what does this change of basis mean? It is just a different way to write a vector, and often it is easier to use specific basis in certain cases. So we're going to change the basis. You know, you got your standard basis. It's really nice. 1, 0, 0, 0, 1, 0, 0, 0, 1. These are great little vectors here, and it's really easy to create vectors off of them, and it's real obvious and easy to explain it to others where these coordinates are coming from, because you get the same vector back again. But we want to change the basis so we can kind of basically disguise what we're actually manipulating here. You got to know the basis. If you got the basis, that's your code. If you got the basis, you got the elements of the code, and then you can put the coefficients in front of it and recreate whatever vectors you need to have. This is our goal with this stuff, with these coordinate vectors. So turn the page. Here's another one. So, I mean, again, I'm starting small here because, honestly, this stuff can be rather difficult. So, let's let B be equal to two vectors, B1, comma, B2. A basis for R2, where, I'm going to give you the basis. Here's my code. B1 is going to be the vector 0, 1, and B2 is the vector negative 1, 1. So these are not my standard bases. Does that make sense? So this is a basis for R2, okay? 0, 1, and negative 1, 1. And I'm going to let vector X be equal to 2, 3. This is my vector X. I'm telling you, those are my credit card numbers. Okay, it's a very small credit card. 2, 3 is my code for my credit card. All right, you with me so far? All right, now, I want you to find the coordinate vector X relative to this basis. So, just to be able to find this, okay, here's what we're going to do. We're going to sit there. I am looking for a vector, and it's going to be a C1, C2 vector, okay? And this, basically C1, C2, which are the coefficients, C1 times B1 plus C2 times B2 is equal to the X vector. These are coefficients. The problem with this world is going to be it's hard to distinguish the coordinates and the actual vector itself, because they're going to be the same size. But when you don't have the standard bases, they're going to be different. There's my hacker's nightmare right here, that they're trying to hack through this stuff. So how do I solve this thing? So in other words, let's talk about it. I want C1 times B1 vector, which is Z1 plus C2 times B2 vector, negative 1, 1. And I want to be equal to the X vector, and my X vector was 2, 3. And I'm doing this on a small scale so you can follow along, honestly. Now, how would you solve this thing? Well, lots of different ways you can look at it. You can write them as equations if you want to. C1 times 0 plus C2 times negative 1 is negative C2 is equal to 3. And you got the equation C1 plus C2 equals 3. So you can write them as system of equations. You can write them as a system of vectors. You can write it as a matrix. Matrix would be 0, 1, negative 1, 1, multiplied by C1, C2, and it's equal to the X vector 2, 3. So you see what I'm talking about. There's 3 different ways. All these different ways are the same thing. My goal here is to solve for C1, C2. Now, being this is called linear algebra, my recommendation is look at the matrix. How would you solve this matrix equation? What have we been taught already to solve a matrix equation? What are you going to do? Tell me what to do. How do I solve this? Solve for C1, C2. Very good. Solve for C1, C2. You mentioned the word augment. So what do I end up getting? 0, negative 1, 1, 1, augment with 2, 3. Does that make sense? Okay. Now, how are you going to solve this thing? What do we do? Well, what's your first move? Now, I'm trying to solve this thing, so I'm going to go for my famous reduced row echelon form. So I like to have that 0. I like to have it a pivot. How are you going to make it a pivot? What's your first move? Swap. Row swap. Okay, there's only 2 rows. That would be row 1 with row 2. So this would give me 1, 1, augment 3 with 0, negative 1, 2. Now, what's your next move? I already got 1 there, and even better, I got a 0 right there. What's your next move? I want to make this guy a pivot. So what am I going to do? Negative 1 times row 2. This would give me 1, 1, augment with 3, 0, 1, negative 2. And now I've got one more move to make, which is this. I'm going to sweep up and go negative 1 times row 2, add it to row 1. Whatever row I add to, I replace row 1. This would give me 0, 1, negative 2. So just negative this and add. So negative 0 plus 1 is 1. Negative 1 plus 1 is 0. Negative, negative 2 plus 3 is actually 5. So there we go. So this automatically tells me that C1 would be equal to 5 and C2 equals negative 2, which means 3 dots in a triangular fashion means that the coordinate vector of x relative to this basis b is this correspondent vector 5, negative 2, the coefficient vector 5, negative 2. Does that make sense? So, and we got our answer. Now I want to look back at the algorithm that I just did so I can talk about it. Okay? So here we go. What did I do? To create this column matrix here, what I did was I took, and there's some notation here, this matrix P with a subscript beta. This is your matrix of basis, your basics matrix. You augmented it with the vector, so this right here, you took the matrix P relative to basis P, augmented with the X vector, you reduce row echelon form, the P will turn into the identity, and the X will actually turn into the X corresponding with the coefficients of the beta. That's exactly what we did here. So think about it. We did this, This is your basis matrix, and order matters. This was the 0, 1, negative 1, 1. So this is the P relative to B. We augmented it with the X vector, which was given to us to be 2, 3. I reduced row echelon form this stuff. I end up getting 1, 0, 0, 1, and then I got this number over here. I got, what, 5, negative 2, which told me that the X vector relative to B is the coefficient of 5, negative 2. This is the algorithm which I did. Does that make sense? So, what if I want to go the other way, okay? So, in terms of this, look at this particular equation. This right here, this was your P relative to B. This was the 0, negative 1, 1, 1 matrix, multiplied by the X coordinate matrix of coordinate vector C1, C2 was equal to the X vector, which is 2, 3. So this and this are equivalent to each other. This is what we're doing. This is the actual matrix equation. Think about it. So you take this new, and we talk about a matrix, this P relative to basis B. This is basically taking your basis matrix and finding them as a column matrix here, okay? Multiply times your coordinate basis, and it gives you the vector. So, based upon what we're just discussing, in this example, what is my matrix P relative to basis B? What is that matrix? It is the matrix 0, 1, negative 1, 1, and I'm reading it in terms of columns. That's my P matrix. Does that make sense? And remember, it's coming from, this was B1, this was B2. This is how I created this guy. But we're creating this system of equation type thing here. So, keep it going here. So, boom, 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 boom. What's the next thing we're going to do? Putting this all together, we have this. Quote, the change of coordinates matrix. That's this P thing that I'm talking about. I wanted to wait and give you a fancy word for this, but it is the change of coordinate matrix. This P sub B. Now you got this basis, B1, B2, Bn. This is your basis. So the actual change of coordinate basis is a matrix with the columns being your basis elements. There's your B1 vector, B2 vector, B3 vector, the Bn vector. This change basically the B coordinate vectors to the standard basis. When we went to the identity, when we reproduced this stuff, basically this is the P sub B. This is to change from coordinate vectors to the standard basis. So, and we had this little formula which we just wrote up. I'm just rewriting it again. X is equal to this coordinate basis matrix, P sub B, multiplied times the coordinate vector X relative to basis B. So you notice these bases match up here. This is matrix P times vector X. And relative to B, this will give me my coordinate basis, my coordinate vector, and this is my vector, actually, my vector. But any vector that we talked about before is always in standard form, you know, the standard basis, 0, 1, 1, 0. So you can just read off the coefficients. That's basically in the clear, if you will. Now, so we have this equation to go from x vectors to the coordinate of x vectors relative to basis B. This is the mathematical formula. But sometimes you want to go forwards, other times you want to go backwards. So I want to figure out what this x relative to basis B vector is going to be. So all I need to do is think about it from a matrix perspective. How do I get rid of a matrix? You can't divide by a matrix. That's illegal. But what gets rid of a matrix? The inverse. So I can multiply by the beta inverse on both sides. Okay? Now, here's the deal. Multiply by the inverse on both sides, I end up getting that the x coordinate vector basis relative to basis b is equal to v basis inverse times the x vector, okay? Now, why am I allowed to have this guy right here, B inverse? Why does B inverse exist? Does B inverse always exist? P inverse relative to V. Well, because the columns are linearly independent. Does that make sense? You know, we're always going to have an invertible matrix. Well, I'll use that always in terms of questionable stuff here. As long as you're actually dealing with Rn and dealing with, we got the same number of vectors as we do equations, okay? Got to be careful on this one. What if I'm doing a subspace? And you know, I got H, and it's a subspace of R4. But H only has 3 vectors in it. So what size matrix would this P matrix be? I've got, now think about it, they got 4 components in each vector, right? But I only got 3 vectors. So what I'm going to have here is going to be a 4 by 3. Is that going to be invertible? Why not? What do invertible matrices always have in common? They got to be what? Square. As long as this P matrix is square, then it's invertible. Okay? Is always invertible as long as it is square. And why will it always be invertible? Because as long as it's square, you can find the inverse, but because the vectors, which are the columns, are linearly independent, and it's square, you can always find it'll be invertible. Does that make sense? All right? So, that's the big idea behind this. So we're writing these guys as equations. X equals your basics matrix P times the coordinate vector relative to beta. And so that means X, the coordinate vector relative to beta, is equal to P inverse matrix times the actual X vector. So you can go backwards and forwards on this thing. So what we're talking about here is quote-unquote coordinate mapping. So what exactly is this coordinate mapping type thing here? So you've got this basis, beta, which is B1, B2, dot, 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 to Bn for some vector space V. And this puts a coordinate system into V relative to basis B. So we have this mapping. We're taking X and we're mapping it into a coordinate basis. We're disguising it. Think about it. Okay, so X, we're going to map it over here to the coordinates of X relative to basis B, and this is called the coordinate map, and it goes from vector space V, because X comes from any vector in V, into Rn. So you can go from any arbitrary vector space, and we're going to kind of map this stuff over into Rn, and this because they're in components and in coefficients of your vector. Okay? So, got to give you some examples, but first, a theorem. But again, I'm trying to make this stuff kind of exciting for you guys, especially knowing what your majors are. We're hiding stuff. So, in that concept right there, a lot of people look at this particular section and they get confused because they're not following along. And I think the reason why they're not following along is because they're missing the point of this stuff. The point of this stuff is to basically rewrite a vector relative to a basis. So the vector is going to quote unquote change to a coordinate vector, and so it's hiding what the vector really is. So you've got to know what the basis is, and you need to know what the coordinates are, the coordinate basis, so you can get back to what the original vector was. And again, I remind you, crap like your credit cards. Now, in the old days, we would discover this and really study this stuff from a military perspective. Hiding, code theory. We want to hide this stuff. We want to know what this stuff is, but we don't want our enemies out there to figure out what it is. And so I've got to send out my messages, and it's got to be in code. But for every code I put out there, my guys in my field must have the inverse code so they can, basically go back and basically rewrite my coded message back into the clear so they can read the message, and then they would respond to my message, code that, send it back to me, and I would do the inverse on the code and be able to understand this material. Now, that was great in the good old days of the militaries, and you get some great historical aspects, like the first major deciphering stuff would be like a Caesar cipher. Julius Caesar used to do this in the field when he was battling the Gauls up there in Germany and stuff like that. He would send messages to his generals as they were doing maneuvers. He would do what we call a Caesar cipher. He would take the Roman alphabet and just basically shift it over about 3 or 4 letters. But when he wrote up words, it looked like garbage because no one could follow it. But if you actually just take the letters and just go back 3 or 4, whatever the code was for the day, you can put the words back into readable stuff. So his generals could see this stuff. But if the message fell into the Germans' hands, well, they wouldn't be able to read it. Okay? So that's your first type of what we call a Caesar cipher. And then from that, we go through a bunch of historical things about how to disguise stuff and code stuff. But throughout the ages, it's always been more of a military perspective, up until about the 20th century. 20th century, well, there you go. We started to do, banking and basically, sending funds, wiring funds, the invention of the telegraph machine, and you have to send off your information so the banks can, transfer funds from one bank to another and things like that. So really around the late 1890s all the way up through pretty much to today, this idea of not just the military's interested in this stuff, the banking industry and so many other things. Now, don't get me started on modern day credit cards and stuff like that. That's basically where it has formed into. But, I mean, even, for those people that are interested in military history and like the Enigma machine Germans during World War II, that original Enigma machine was a banking machine that went from one bank to another and transferring funds and wiring bank accounts and stuff like that. That's where it started from. The Germans discovered in World War II and thought it was great, and basically set their whole entire military based upon the concept. And it was a very mathematically advanced system, and it's when the modern day of computers started to take apart so we could break their code and defeat the Germans in World War II. So this stuff is really that idea of hiding stuff. So I'm trying to get you motivated in terms of why you need to know this code theory that we're doing, this coordinate mapping type thing here. So switching that over and getting you guys well motivated for this particular material. All right. So here we go. Theorem. Let beta be a basis, B1 vector, B2 vector, ... Bn vector, okay, be a basis for a vector space V. Then the coordinate map from vector x to the coordinate of x relative to basis B is a one-to-one linear transformation. See all this stuff coming back and honing you now? It's a one-to-one linear transformation from vector space V into Rn. Now, when your vector space is Rn, you're basically just coding in vectors. But vector space V does not have to be Rn. We're just going to code over. These are coordinates, so they're going to be coming from n-dimensional vector spaces. That, if you go back and see if I still have it up here somewhere, this is why I did this problem in the beginning. Because you're thinking, like in the last example, it was R2 and everything went to R2 is R2, and it's kind of hard to figure out. If you go back and look at this example, the first one that I did, this was vectors in R4, right? I just created vectors based on R, but it's a subspace of R4, only using 3 vectors. So because this is R4, these have 4 components in it. But the coefficient or the coordinates of x relative to the basis B, because the basis only has 3 vectors in it, it's going to be a, this is an R3 vector. This is coming from R3. There's only 3 components. So that n number happens to be the number of vectors in the basis. That n number and that n number in terms of number of vectors in the basis, that's what's matching up to this stuff. So here's an example of, they're not always the same. My vector is from R4, but the coordinate vector is actually from 3 because I only got 3 vectors in the basis. So it's not always the same, but a lot of the times it is, and you get confused on that. So keep going here. So I've got to create something that is a little more bizarre for you. So here's an example here, okay? Here we go. Vector space, P3, is the polynomials a0 plus a1t plus a2t squared plus a3t cubed plus plus, and we stop, a3. So degree 3 is what we get. So the AI is coming from the real numbers. And we're going to use the standard basis, 1t, t squared, t cubed. This is polynomials, okay? So if P of t is an element of Pn, then P of t is going to be a1 plus a2t plus a3t squared plus a2t squared plus a3t cubed, okay? I started with a0, so there's actually 4 of these guys in there. So P relative to basis B would be this, a0, a1, a2, a3. This is the coefficient of 1, this is the coefficient of t, this is the coefficient of t squared, this is the coefficient of t cubed. Here the coordinate mapping is from P to the coefficients P of t, and it's a 1-to-1 linear transformation from P3 to R4. Think of the coordinate mapping as just a different way to rewrite the objective, which is the vector. We're rewriting this stuff, but you guys need to be thinking of it from a code theory perspective. So here's another example of going from polynomials to vectors and how they are, quote, disguised and stuff like that. This one is not big in terms of my disguising, but later on it can very well be. And we'll talk more about that next time. So next time we'll work on the rest of these guys and move on to section 4.5 and 4.6 and finish up chapter 4. So study hard and see you guys then.